So hi everyone, in this video we are going to talk about semaphores. So in the past videos we have discussed about mutex locks, and the mutex locks are one of the simplest of synchronization tools. In this video we are going to discuss about semaphores, in which these are more robust tools compared to mutex locks. They behave similarly like a mutex lock, but can provide more sophisticated ways to synchronize activities. So what is indeed a semaphore? A semaphore S is an integer variable. So take note, integer variable that apart from initialization is accessed only through standard operations, wait, and signal. So wait and signal are originally called as P and V. So where did this original terms come from? So wait was originally called as P, which means proveren, which stands for proveren, and proveren means to test. So in other words, what we are doing here is testing whether a certain resource is available or not. Signal, on the other hand, was used to be called as V, which stands for Verhoeven, or I don't know how to pronounce it exactly, but it means to increment. So once a certain process has released a certain resource, so then we can add one or increment our semaphore S by one to indicate that that resource is already available. All right. So the semaphores can be used to control access to a given resource consisting of a finite number of instances. And the semaphore is initialized to the number of resources available. So let's say we have two CPU cores available. That means that the semaphore S is initialized into 2 because those two CPU cores are the resources that are available. So if we want to use a certain resource, we use the wait operation. But if we want to release a certain resource, or let's say a certain process is done executing a certain process that uses that resource, so it lets go of that resource. So we use signal. So semaphores can be used to solve various synchronization problems, in which we will discuss in the next videos. So this includes the bounded buffer problem, the dining philosophers, the readers writers problems, etc. All right, so we will go back to this later. So for instance, we have two processes, P1 and P2. So we have for the P1 and the P2. So let's say the P1 is still executing. So you can see that there is a common variable here, sync. All right. So if P1 is still executing, that means that P2 has to wait. And if P1 is done with its execution, it sends a signal that it is done with its execution. And so then the P2 will quit waiting and perform its own operation. Okay, so semaphores provide mutual exclusion for a certain process. So assuming that we have this do while loop, right, and it contains this code. We have the wait, and then critical section, and then the signal. Okay, let's start with this part. So instead of S, we use here, let's say, mutex na variable, semaphore mutex. And mutex is initially stored with a value of 1. Okay, that means that we have one resource available, right? So if a certain process wants to execute or to enter its critical section, it will check this wait operation, right? It will check this wait operation. So if a certain process, other na process is in their critical section, then we will have to wait. So if the other process has quit executing its critical section, then this certain process can enter its critical section, right? And once this process is done executing, then it will send a signal and it releases that resource. Okay, so we will understand this more with a subsequent na example. So assuming that we have this common variable semaphore S. And as mentioned, this S is initialized to 1. So these are the standard definitions of the weight and the signal. So again, if you want to use a certain resource or if you want a certain process to enter its critical section, um, we use the wait na operation. But if you want to let go of a resource or to release a certain resource, we use the signal na operation. Okay, so you can see that in these operations, there is the common variable na S. Okay, so we can think of it like a telephone booth. So this telephone booth is the shared resource. Okay, and the semaphore S is an indicator whether this certain resource is available or not. Okay, so we can also think of it like in this definition of critical section, right? If we have the certain process which is in its entry section, whether that process is in its critical section or in its exit na section. Okay, so we will do this one by one. So initially, this S is initialized to 1, meaning we have one telephone booth that is available. Okay, or one telephone booth that is not used. Okay, now in the wait na operation, we can see here a while na loop. And while the semaphore S is less than or equal to 0, that means that if S is negative or 0, then no operation is performed. So in other words, what it means is that that certain na telephone booth is used by other processes. Okay, that means that we have to wait. This loop will not stop. Okay, we have to continue waiting because this telephone booth is used by some other process. So you can see that Santa A is already using this booth. So that means that the Santa B has to wait until Santa A is completes using this telephone booth. And you can see that the S is also 0. That means that there is no telephone booth that is available as of now. Okay, so it means that in OS na terms, it means that some other na process is performing their critical section. Until then, we have to wait. So in this case, Santa A is still using the telephone booth. So Santa B has to wait until Santa A is done. All right. So you can see here that immediately there is a semicolon in this while loop, meaning we do nothing. We do nothing while S is less than or equal to 0, while this is true, or some other process is using this telephone booth, or some other process is in their critical na section. Now, suppose that Santa A has left. So this telephone booth is now available. That means that we add 1 into the semaphore S. So when Santa A has left, it sent a signal that it is done with its critical section. And so it adds 1 into the semaphore S. So some signal that a process has finished its critical section. And after executing its critical section, S will be incremented by 1. So as you can see, since S is now incremented by 1, it means that we have now 1 available na resource. Now we go back here. And the Santa B was still waiting, right? And now it is true because S is less than or equal to 0. Actually, this should be false na, no? This should be false. This should be false since S now is equal to 1. So let me just change this. So this should be false now. So this is now false because S is equal to 1 and it is not less than or equal to 0. That means that 1 telephone booth is now available. So Santa B can now enter and quit waiting. So we are also out of the loop. So now we also decrement the S by 1. Decrement S or subtract S by 1 because Santa B has quit waiting and took its turn in its telephone booth. So nung ginamit na ni Santa B yung telephone booth, so obviously this resource is now no longer available. Okay, and then the S is now equal to 0, right? So do you get the idea? So going back here, so if S is equal to 1, that means that the telephone booth is available. And if while S is less than or equal to 0, meaning this telephone booth is not available. So, or we don't have any resource that is available. So we have to keep on waiting, and this loop will continue looping. And Santa B will have to wait since we don't have any available resource. And Santa A has left. So Santa A has sent a signal that it is done with its critical section or done using the telephone booth. Okay, so we increment the S by 1, and that means that we now have an available resource. And so then the Santa B is done waiting. Since we now have an available resource, we are out of the loop. And when Santa B took its turn and used this telephone booth, we decrement the S by 1. Okay, so as you have seen, S is the common variable for all the processes, and all modifications to the variable S must be done indivisibly. So that means that if one process is modifying the semaphore value, then no other process can simultaneously modify that same semaphore value. So in short, it is non-preemptive. So there are different types of semaphores, not really a lot. We only have two. We have the binary semaphores and the counting semaphores. So what can you deduce from the binary semaphore? So from the term binary itself, that means we only have two. Okay, we only have two values. So the binary semaphore is an integer value that can range only between 0 and 1. So it is easier to implement compared to counting semaphore, wherein the counting semaphore is an integer ranging over an unrestricted na domain. So simply said, it is the number of resources. So if we have the binary semaphore, so that means that we only have, in the previous example, one resource available. So the value of the semaphore can only be either 0 or 1. Is it available or not available? But the counting semaphore is equal to the number of resources. So that means that if we have 5 telephone booths, then the semaphore S will then be equal to 5. Okay, so the binary semaphore is also known as the mutex locks, as they are locks that provide mutual exclusion. And we can use this binary semaphore to deal with the CS or synchronization of problems for multiple na processes. So the end processes share a semaphore in which we term as the mutex, and we initialize it to 1. Right, so let's start with the binary semaphore. So you have already, I assume that you already understand what semaphores are. So let's see what this binary semaphore is. So again, this weight of S works only if the semaphore is 1. So otherwise, it gets stuck into the while loop. So you have already seen this earlier. Okay, so and the signal succeeds only if the semaphore is 0. Okay, so let's have an example. We have two processes here, process 1 and the process 2, and in which each process has the weight and the signal operations. Okay, we have a common variable S, and S is initialized to 1. So in other codes or resources that you can see, instead of S, they are using mutex. Okay, they are the same thing. Okay, they refer to the same idea. Okay, so assuming that we have semaphore S is equal to 1, that means we only have one resource na available that will be shared between two processes, process 1 and process 2. So assuming that process 1 wants to enter its critical section, so now the P1 is here, and it checks here if S is less than or equal to 0. So S is equal to 1, and 1 is not equal less than or equal to 0. So this is false. That means that no other process is in the critical section. So that means that process 2 is not in its critical section yet. In other words, since we only have two processes for now. So that means that since this is false, so it breaks out of the loop and proceeds to using that resource or entering its critical section. So since nandito na siya, so the S is decremented by 1. So S is now equal to 0 to indicate that no resource is available for now. So now the process 2 also wants to enter its critical section. But when it checks here, S is equal to 0 as of the moment since P1 is in its critical section. All right. So that means that this while loop will evaluate to true. So this will keep on looping while P1 is still here. All right. So since this is true, so process 2 is in its busy waiting state. Okay. So now, assuming that P1 is already done with its critical section and is now on its exit. So P1 sends a signal and S is incremented. So now from 0, S is now equal to 1. That means that we now have an available resource that. And so process 2 can now enter its critical section. So that means that this now evaluates to false since S is now equal to 1. So that means that P2 can enter the critical section. And since P2 is in its critical section, so S is also decremented by 0, as you can see here. And assuming that P1 also wants to enter the critical section again, so since nandito si P2, si P1 has to wait. All right? So what about the counting semaphores? So integer value semaphore S is greater than 1. So as mentioned before, if we have 5 resources available, then the semaphore S is also equal to 5. So the semaphore count is the number of resources available, and that is used to coordinate the resource na access. So if we add more resource, the semaphore count is also automatically incremented. And if the resources are removed, or if a certain resource is removed, then the count is decremented. So based on the resource count, the number of processes are allowed in the critical section. Hence also, the wait and signal operations are uninterrupted. So if you want to have an animated version of this, you can watch this YouTube video. Okay, so you can think of it like this. So we have S equal to 4 initially. And as more people are using the telephone booths, so the semaphore S is being decremented. But every time a person comes out, then the S is incremented. Okay, so let's have an example here. We have 3 processes, process 1, process 2, and process 3. So assuming that the S is initialized to 2, that means we have 2 resources available. Okay, so now process 1 wants to enter its critical section. So 2, we have S equal to 2. So is 2 less than or equal to 0? So since this is false, that means that we have 1 resource. We still have 2 resources available. So that means process 1 can enter its critical section, and we decrease the S by 1, indicating that we now have 1 resource available left. Okay, so now process 2 also wants to enter its critical section. So we have available resource equal to 1, and 1 is not less than or equal to 0. So this is false. And it breaks out of the loop. That means that process 2 can also enter its critical section. So since P2 is in its critical section and it's using the shared resource, so we also decrement the S by 1. Okay, and now process 3 also wants to enter its CS or critical section, but we no longer have any resource available. S is equal to 0. So this is evaluated into true. So that means that P3 or process 3 has to wait This will not go out of the loop. Will not break out of the loop while this is true, while P1 and P2 are executing their CS or critical section. Okay, so now assuming that P1 is done, so it's now in the exit section. So it sends a signal and S is incremented. That means that one resource is now available. So now this becomes false since we now have resource available. So it breaks out of the loop P3 and enters the critical section, and then S is being decremented to indicate that we no longer have resource available since P2 and P3 are in their CS or in their critical section. Okay, since we have S is equal to 0 and P1 also wants to enter its critical section again, but at this time, there are no available resource. So P1 or process 1 has to wait. Okay, so that's it. So assuming P2 is done, so P1 can also enter the critical section since we now have available resource. Okay, so that's it. We'll discuss this topic in the next video.